Yo, what's up everyone? Today's video we are going to quickly complete the chapter uh, electrical circuits. This is a very important chapter in an examination, and I have already made the videos of Kirchhoff's laws and signifying one example already. So we are going from 14.1.2 to 14.6.2 in today's video. So before we start, if you have not watched the earlier video, I strongly recommend you watching it, because you might not understand how does the balanced condition of the Wheatstone bridge is going to work if you don't know what are the two laws. So first let's go with Wheatstone bridge. So what is Wheatstone bridge? Wheatstone bridge is not a device. Do not make that blunder. This is not a device. This is an arrangement. This is an arrangement of resistances in such for the arrangement of let's write uh, three known and one unknown resistance for the uh, purpose of determining the unknown resistance in terms of the known resistances. That is how you can define a Wheatstone bridge. And how it does this look like, I'll show you a small figure. Look at this. This is a simple Wheatstone bridge. This is a resistance P, Q, R, S. There are or you can whatever write it, it does not really matter. Let's go like this. Okay, so this is our Wheatstone bridge, and the principle of the Wheatstone bridge is very simple. It states that the principle of Wheatstone bridge state that if the galvanometer shows no deflection, that is, if they are in the balanced condition, then the opposite arms resistances are equal. That means PR will be equal to QS. You get me? QS. PR will be equal to QS, or PR will be equal to QS. So that will give us P by Q equal to S by R. We will get that. The balanced state. That is the balanced condition of the Wheatstone bridge, and that is also the principle of Wheatstone bridge. And we are also going to prove it all today, right now. So first up, let's start with the figure. We're just making a new good figure, and the principle. Let's write the principle first. Principle of Wheatstone bridge. At the balanced condition of the bridge, the product of resistances of opposite arm are equal. That is, when there is zero current, the PR will be equal to QS, or P upon Q will be equal to S upon R. This is the balanced condition of the Wheatstone bridge. You need to know that. Now then, let's make a bigger and a more visualizable figure. These are the two resistances. This is the third one. Oops, I think I messed up. Yeah, I just don't know how to draw resistances. I'm sorry about that. Look at that. Now we are naming this P, Q, R, S. This be point A, point B, point C, point D here. We don't need this, by the way, so let's just assume it is E and the current is going like this because it flows from positive to negative terminal. So yeah, so imagine a current I is going and it will break here to 2 points, I1 and I2. Here I forgot the galvanometer, I'm sorry about that. Look at that. Ig goes below and I minus I1 minus Ig goes in this way. That means, what does that mean is it comes in and then I2 goes here, the Ig current comes here, adds up with I2, and this will be I2 plus Ig, and when you add this again I will come here because I1 plus I2 equal to I will come here. Now we write everything in language. Consider a Wheatstone circuit as shown in the figure. As shown in the figure above. P, Q, R and S are resistances of same order. G is the galvanometer. Galvanometer. The battery of EMF E is also placed. The battery of EMF E is also placed. And I be the current flowing through the circuit. Then we know that from Kirchhoff's current law, the first law, we know that the second law, Kirchhoff's voltage law, at a loop. We need to take a loop. So we're taking a loop ADBA. Let's take the direction of current like this in the both of these loops. We can take that ourselves. So at a loop ADBA, what is going to happen is very simple. At ADBA, right? So the sum of, from the KBL, we know that sum of EMFs will be equal to sum of IRs. That is, it will be 0 equal to IR. How many IRs are there? I1P plus G is also resistance, by the way, so it will be IgG plus, it is positive, right? Because it is, oh nope, it is negative. Like this, it is also negative. And the next thing like this, then it is yeah, it is positive. I2S is positive. If you don't know how to check this, it is a very deep concern. You need to go to other YouTube video to learn this, so I'm sorry for that. And after that, I'm just kidding, bro. I'm just kidding. I'll teach you, of course. You take any direction. And in that direction, look at this. It is going through this, right? So circle the direction of circle. I'm taking anti-clockwise. That means it should be like this. If this matches with the direction of current, that becomes positive, and if this direction does not match the direction of current, that becomes negative. That in other words, this is not being met, but this is being met. It is parallel, it is anti-parallel, that is why it is negative. Okay, now we're moving on to the next portion. If we simplify this, it will be I2S will be equal to I1P minus plus IgG. Let this be equation 1. Then we go at a loop from the KVL as well. At the loop BTC B, C, D, B. At this loop, also the same thing will happen. There is 0 will be equal to here. The direction is positive to the thing, so IgG plus I2G plus IgG, and it will be opposite to only this, minus I1Q plus IgQ. That is what is that is what's happening. Yeah. So then, at the balanced condition, what will happen at the balanced condition? We said earlier, at the balanced condition, no current flows through G, that is Ig equal to 0. Then equation 1 becomes I2S equal to I1P. This is equation third now. This is the equation second, and this equation becomes Ig. This becomes 0. This is 0. This is 0. And this is 0. This is 0. So it will be I2G will be equal to I2. What the hell? I2G can be possible. It's IgG. My bad. Wait. There is some error here. IgG. This is I2R. This is I2R. My bad. This is also R. My bad. This is not 0. Yeah, this is 0, but this is R. So I2R will be equal to I1Q. This is equation 4. Now if you dividing 3 by 4, you will get I2S by I2R equal to I1P by I1Q. That is P by Q equal to S by R, which is the balanced condition and hence proved. So we have successfully proved the Wheatstone bridge principle. We proved that Wheatstone bridge is a real thing. Now there are some numericals, of course, related to this, and before all that, there are some short questions as well, very important short questions. And let's see. The first question is, when is Wheatstone bridge most sensitive? The answer to this is very, very, very simple. When all the four resistances are of same order, the bridge is most accurate, most sensitive. Question number 2, why is Wheatstone bridge not suitable for measuring very high and very low resistances? So why is it not accurate or used to do it? So for very high resistance, galvanometer also must have high resistance, which means it draws current, and very low current will flow through it, just like that. And due to insufficient current, because current and voltage, the resistance and current, because through it, so because what I was gonna say, because so it becomes insensitive. So galvanometer becomes insensitive for very low resistance. The resistance of the wire itself also can't be neglected, bringing error in the measurement. Okay, now that we know this much, we are going to now do some numericals of this. So yep, the question says, in the given Wheatstone bridge diagram, calculate the value of I1, I2 and I. Very very simple numerical. In the given Wheatstone bridge diagram, calculate the values of I1, I2 and IE. The diagram given is the basic Wheatstone bridge diagram. Like this. E is given 1.5 volt, which is not even required, I think. And this is given 50 ohm. This is given 5 ohm. This is given 6 ohm. This is given 60 ohm. I goes from here and splits to I1 and I2, and that's all it's given. And there is a galvanometer, just like that. Now yeah, we need to understand what's happening here. We need to assume, we need to find out if it's in the balance condition or not. Since we have all the resistances, we can write down here P equal to Q equal to R equal to S equal to P equal to 5, Q equal to 6, R equal to PQR equal to 60, and that equal to 50. So that is P by Q equal to S by R, or P by Q is 5 by 6 equal to 5 by 6, R by S, sorry, S by R, right? No, R by S, my bad. We just proved here, by the way. I'm not trying to do anything. We just proved here S by R. S by R 5 by 6, just like that. So it is true. Then Ig will be equal to 0. No current flows through G. Then from KVL, from Kirchhoff's voltage law, at a loop, name them A, B, C, D. At a loop A, B, D, A. Let's take this direction anti-clockwise, just like earlier. And then the summation of E will be equal to summation of IR. Summation of E will be equal to 0. Summation of IR, however, will be equal to minus 5I1 minus 5I1 plus 50I2, or 5I1 equal to 50I2. That's it. And or let's find out I1 equal to 50 by 5 by 50, that is 10I2. So, and again at a loop B, C, D, B, you do the same thing. 0 will be equal to 60 into what comes here is I2 only, I2. 60 into I2 minus, wait, no, I think it will be positive. We're taking this direction, or it will be negative. Minus I1 into 6. 6 I1 equal to 60 I2. Now we have we came to the same fucking thing, bro. What the hell? I1 equal to 10 I2. So if you cut this with 10 and this is 10 bro, what the hell? We just proved something. I don't want to do that, bro. So if you don't want to do that, don't be dumb like me. Just use a Kirchhoff's current law. Now from KCL we have I1 equal to I1 plus I2 at a junction A. So I1 plus I2, that means I1, what is I1? What is I1? 10 I2. So I1 plus 10 I2. 10 I2 is I2, so it will be I2 plus I2. So I equal to 11 I2. We have this equation, and we have let's find out I2 in terms of, okay, yeah, we have this thing right now. So this is not enough, we need something else, we need the value something else. So we have to take a bigger loop as well. So we are taking the loop with EMF, this loop right here. So in this loop, at a loop A E F, oh no, at a loop G E F H G, oh no way, at a loop G E F H D A G, G E F H D A G. At this loop you can do it whatever. And in this loop, look at this, sum of EMF is 1.5. let's take this let's take this, then it will be negative because it comes out from the negative terminal. So minus 1.5 equal to yeah, this will be positive, minus 50 I2 plus 60 I2. Crazy. Okay, now we can find the value of I2 very simply from here. Minus 1.5 equal to minus 10 I2. I2 will be equal to 1.5 upon 10. 1.5 upon 10 is 0.15 amperes. I2 equal to 0.15 amperes, and this value you can put in here to get I equal to into 11, that is 1.65 ampere, and you can again put this value right in here to get I1 equal to 0.15 into 10, that will be 1.5 amperes. So we know the values of all the things. I1 equal to 0.15, I2 equal to 0.136, and I equal to that. So you can do it in this way. Now after that, what we can do is go to the next topic, that is the meter bridge. Oh yes, meter bridge. Okay, you got visible, you can check it. Okay, now we're going to meter bridge. By the way, if I'm doing anything incorrect, you can please let me know. I'm not doing it everything correct, probably not. So if I made any mistakes or whatever you find out, you can tell me in the comment. Meter bridge is whatever you say. Meter bridge is a device now. Wheatstone bridge was a concept, was an arrangement of the resistances, but meter bridge is a device used to measure the unknown resistance. Meter bridge, a device used to measure a known resistance based on the principle of Wheatstone bridge. So this is the thing. Now the meter bridge is a bit different from the Wheatstone bridge. How is it different? Because it is a device. Actually, it is a device, so it has to be different, right? Yeah, somewhat it has to be different, but not by a lot as well. So let's draw its figure, which is not so significant but very easy, so you can just draw it. First of all, think of how was the thing, the the potential, what is it, bro, the Wheatstone bridge. It did not had anything, but since we already say the name suggests meter bridge, we already know there is something called a meter. So let's draw a meter scale. Draw a meter. Draw a scale that is exactly 1 meter long, just like that. A scale that is 1 meter long, and connect it with some wooden pieces, just like this. Just like this, you can do it, right? And then add a circuit below that. What do I mean? Let's put something like this, like connecting places, and put a circuit behind below it. Also put a key so that the thing can be controlled. The this is a key, and this is the, yeah. Now the length here, this length must always be 100. Yes, this length must always be 100 centimeters. 100. This is always 100. Every single day, that's 100. Got it? Right. Now, the wooden things need to be connected to resistances, so you make a gap 1 right here, like this. Gap 1, just like this, and again one more gap for the resistance box here, so make another gap, and you can just connect this. Yeah, this is the figure you need to remember. This, this, this. And you need a jockey, so you put a galvanometer and a jockey in the scale J. The length from either side is L, and this is 100 minus L, obviously. So yeah, now from here you take the resistance X to be determined, and you put a resistance box here. Resistance box, and this is R, or S. This is X or R. I mean, this is X or S. This is the resistance to be determined, and this is the figure of meter bridge. This is the figure of meter bridge. Look at this. 1, 2, 3, 4. There are 4 resistances. Everything's clear, right? All right, all right, all right. So you can write every single thing yourself, but still I will be writing somewhat. I already wrote definition. Now I'm gonna write the setup. Okay, the setup is pretty long. I'm gonna summarize it real quick. It consists of a uniform wire of length 1 meter, usually made up of alloys. Okay. It consists of a uniform wire of length 1 meter, made up of alloys. It is stretched on a wooden board with the help of with the help of metallic strips. In the left gap, the unknown resistance is placed. In the right gap, a resistance box is placed from which a resistance is pulled out. Galvanometer with a jockey is also connected, and the jockey is slided. What did you say? Slided to determine the resistance. This is moved like this. That's just means it. A battery of EMF E is also taken. Okay, then from Wheatstone bridge principle, we have, what do we have? P by Q equal to S by R. We have this, do we not? We do. From here we find out S to be P by Q into R, right? So where P equal to resistance of wire of portion up to the L. This portion is the P. Look at this, P Q R S. P Q R S. Imagine it. Yeah. Portion this much. Let's name this thing. The one, oh, we cannot label this, but we can name this A B C. So the portion AB, this will be equal to resistance of the, that will be equal to rho L by A. We know that. And Q will also be equal to rho L. Rho L is 100 minus L. Rho 100 minus L upon A. So if you replace all the values, you get S equal to P is rho L by A upon rho 100 minus L by A into R. You cut down the A, you cut down the rho, you get L by 100 minus L times R. This is the standard formula for the determination of the resistance of the unknown resistance using the meter bridge instrument. So now we are doing some numericals related to this specific thing. So yeah, let's start. Meter bridge, question number 1 numerical. Question number 1 numerical. Yeah, look at the question. The question is pretty simple. You can see. You just need to remember, don't confuse by this R and S. The only thing in this is confusion, so you just don't need to confuse it. The thing is, this is always P. The thing that is on the left side of the jockey is always P. This is always Q. This is always R. This is always S. It goes in the order. So the question says, in the meter bridge shown in the figure, the null point is formed at a distance of 60 centimeters from A. If the resistance, this is A and this is B by the question, by the way. If a resistance of 5 ohm is connected in series with S, the null point occurs at 50 centimeters. Determine the values of R. Okay, so there are two cases. Of the first case, at the first case, we have the length. The length, balance length is 60. So let's give this L1 equal to 60. That means the value of P by Q will be equal to, it should be S by R, but here it will be R by S. Why? Because R is this and S is this. So if that's the case, we know that P by Q will be equal to 60 by 40, or R by S will be equal to 3 by 2. 3 by 2. Let this be equation 1. Now for the second case, L2 equal to 50 centimeters. So P by Q will again be equal to R by S. That will be equal to S naught, not S, by the way, not S. It will be S plus 5, because the question says if a 5 ohm resistance is connected in series. In series, you just add it basically. So yeah, that's what you do. Yeah, now look at this, S plus 5, because the question says 5 ohm is added. So it will be equal to 50 by 50. 50 is a new balance length. So that will make it R by S plus 5 equal to 1. Or R equal to S plus 5. Very simple, very sound, right? Now you go for R by S. We need to actually find the value of R by S. So we put the value of R in equation 1. So let this be equation 2. Then we put R equal to S plus 5 in equation 1. That will make it S plus 5 by S will be equal to 3 by 2. Right? So you can cut the S and it will be 1 plus 5 by S equal to 1.5. And if this goes the other side, which is, oh, this is 5. This is 5. If this goes the other side, 5 by S will be equal to 0.5. And that will be S equal to 5 by 0.5. That will basically be 5 divided by 0.5. That's 10. So that will be 10 ohm. Now you put S equal to 10 in equation 2. You just get R equal to 15 ohm, and these are the answers. Very, very simple, very, very easy, as you can see. Now we are doing one more question from this same chapter, from this same type of question, by the way. Okay, let's do the 4 number questions. Right here I'm gonna write. I'm just taking up too much space. So 4 number. Let me quickly write the question, then I'll come back. Okay, here it is. In the given meter bridge experiment, the null point is observed 60 cm away from the end A with X and Y in the position as shown in the figure. This is X and Y, by the way. X and Y as shown in the figure. When a resistance of 15 ohm is connected in series with Y, the null point is shifted towards A by 10 centimeters. Find the value of action. First of all, you need to understand, this is the resistance, this is the P, the Y resistance, this is Q, this is R, this is S. PQRS. Don't forget that. PQRS. So here, solution, if you write down, first of all, the null point is absorbed at 60 cm away from the end as shown in the figure. While it is like this, it is 60. This is 60 here. And when X and Y, when a resistance 15 ohm is connected in series with Y, when, oh my god, which one is Y? I'm sorry, but this one's Y, by the way. Yeah, that's the Y. And when the Y, when a resistance of 15 ohm is connected in series with Y, then the thing becomes that, then the thing null point shifted towards A by 10 means that this subtracts by 10, so it becomes 50. The next things becomes 50, just like this question, exactly the like above question. So in that case, we just do P by Q. Solution, first case, P by Q equal to, what is it, R by S, so Y by X, that will be equal to 60 by 40, Y by X equal to 3 by 2. On the second case, P by Q, right? P by Q equal to Y by X equal to 50 by 50, but it's not Y here, it's Y plus 5, 15. So since it is Y plus 15, oh, I think there is an error, I think. Wait a minute. Yeah, there is a error. What is the error? Look at this. PQRS. If it is like this, then it is X by Y. How is it again? How is it, right? Look at the above question. Look at this question. P by Q equal to R by S. This by this equal to this by this. This by this equal to this by this. So it will be X by Y. So X by Y plus 15 equal to 1. And the same thing happened here. Y plus 5. 15, my bad, 15. Now you put the value of this in equation 1, the equation 2 you put in 1, then you get Y plus 15 by Y equal to 3 by 2. So 1 plus 15 by Y equal to 1.5, Y equal to 0.5, and 15 by 0.5 is 30 ohms of resistance for y equal to 30. And you put now again X equal to Y plus 15, that is 45 ohm. These are the answers. You have done it and I have also done it. So we now complete the Wheatstone bridge numericals as well. Now we are going to basically the most important thing of this chapter. The most important thing of the chapter, but before that we're doing a short question, and we're doing it in the same page right here. Yep, right here in this page. Short question, only one question I have here, and the question is is any change in the balanced condition of Wheatstone bridge seen if the position of galvanometer shifted? You know it, I know it, we all know it. The answer is no. The answer is no. The answer is no, and that's it. So now we are done with this. So we are going on to the most important portion of this chapter, that is potentiometer. What is it? Potentiometer. What is potentiometer? Potentiometer is an electrical device used to determine the internal EMF of a cell. Compare two EMFs of cells and measure the potential difference. Basically, how do you define this is there are two applications of the potentiometer. The first application is comparison of two EMFs of the cell, and it has its two applications. It has two applications to determine the internal resistance of a cell, small r. To do that, its first application, or alternatively to actually to determine the internal resistance of the cell and to compare the EMFs of two cells. It has two applications, so yeah, you can define being based on that application. And so now yeah, so we need to now know the principle of the potentiometer. The principle of potentiometer states that principle of the potentiometer states that when a constant current is passed through a wire of constant CSA, the cross sectional area, then the potential difference across any segment of that wire is directly proportional to the length of the wire. That is, V is directly proportional to L, or V is equal to KL, and K is the proportionality constant, we all know it. Okay, so now we can make the construction. And yes, it does not draw any current out to determine the potential difference. So it is also called ideal voltmeter. Potentiometer is the ideal voltmeter. So if you want to construct a potentiometer, it's very simple. Just draw big this E thingy, and then put an ammeter right here, and then put a key right here, and then bring this like this, and make a bunch of tones here. Look at this. You just make like this, one, make a one, and we make another one, two, we make another one, three, we make another one, four, and wait a minute, 1 2 3 4. Yeah, I think that's it. One, look at this, one, two, three, that, and that, just like that, and connect them. and you put a galvanometer right here, and you also put a meter scale right here. You put a jockey. That's the construction of of the potentiometer, and it's very simple. You can just memorize it by drawing it a few times. I cannot help that. To prove it, you can just use the Ohm's law. To prove it from Ohm's law, to prove the principle from Ohm's law, what do you know? V equal to IR. We know that very well. We do, right? Again, what do we know? That resistance is given by rho L by A. We used it earlier. So put this in above. So V equal to I times rho L by A. Get it? V equal to L I rho by A. V equal to K L, V directly proportional to L. That is the very simple thing you can see right there. And after you prove that, you can say hence proved. But this won't be action or examination, by the way. Now we're going to what will be action or examination. So first of all, we're going to sensitivity of potentiometer, and sensitivity of potentiometer basically means that it is sensitive if it can measure more smaller values. So sensitivity is more if can measure smaller values. That's it. And we have a question here as well. And we have a question here. We have a question. And why is it? Because look at this. If B for B to be small, is directly proportional to L, so L must be large. That's how it's gonna work. So there is a question. What is the question? Is why do we prefer potentiometer of longer length? Potentiometer of longer length than shorter ones. You already know that because sensitivity of potentiometer increases with longer length with length. So for efficient measurement, we prefer potentiometer with longer length. So that's how you can write down, and that will end it. Or if you want to check, if you want to listen to it or look at it once more, look at that. Hope that's enough. And now we're going to potential gradient of a potentiometer. Of a potentiometer. We know that potential gradient basically means this by L, change in the potential difference by length. So this here in we know that this will be equal to rho L by A again by L, right? Is there any confusion? There is not. So this it does not mean that. I'm sorry. K equal to V by L and V equal to IR by L. So K will be equal to I rho A by L and rho L by A. I think rho L by A, and if A comes down, it will be K equal to I rho L by AL, and A, this is cut, so rho I by A. This is the potential gradient. You can define it as potential gradient of potentiometer is defined as the potential per unit length, potential difference per unit length. That's it, of the potentiometer wire. That's it. There is no big deal. You've already learned that before. Yeah, and also yeah, sensitivity also depends upon sensitivity of potentiometer depends upon length of the wire and potential gradient. What does this mean is, if there is more potential gradient, there will be lesser the sensitivity. The gradient should be less for the thing. It is inversely proportional and it is directly proportional. So yeah, that's you need to know. And now we're going to very another important thing, that is applications of potentiometers. What is it? Application of potentiometer. There are two applications of potentiometer. The first application is to compare EMFs of two given cells. So for that you need to first make a potentiometer. We know how to make a potentiometer, do we not? A potentiometer looks like this. Yes, it looks like this, and you have two cells here, so you need to go a bit below. You connect this here, and you have two cells, so you put one cell right here and you put another cell right here, just like this. There is a breadboard type thingy right here, and there are two keys. There are two keys, K1 and K2 here, and only one thing is coming out from here, and there is a galvanometer joining these lines, and the potentiometer wire. This is the potentiometer wire, and there is jockey. This is J1. Let's say this is C, and this is C1. This is C2. Let's say, and that is the figure you need. Okay. Oh my god, I'm making a mistake. This is a resistance, and here is the key K. Okay, so that is all you need. You just need to now write the language to compare. I'm not going to write a lot of language, but you need to extend it in your own words. So yeah, I hope you do it. To compare EMFs of two given cells, E1 and E2. Let's write down E1, E2. The required setup is done. Setup is done. Is made. Is done. The driver cell is E0. Keys K1 and K2 control the flow of current from the cells E1 and E2 respectively. The positive terminals of given cells are connected to the point A, whereas you need to write that whatever you just write yourself. Yeah. They are then connected to the galvanometer, and this is write down. You just write yourself. Then we know that from the principle of the potentiometer, what do we have? What do we have? What do we have? Okay, we don't need to write. We need to write a little bit more, right? Yeah. The principle of potentiometer, when the key K1 is closed, keeping K2 open. That means this won't flow current. The current won't flow here, but the current will flow through here. So if that is the case, then we will have the length of the the potentiometer wire be AB. So first it will be C. So balance point is C. So the balance point, at the balance point, such that yeah, open, then C1 be the balanced point. If C1 is the balanced point, then E1 will be equal to VAC, the potential across AC. From the principle of potentiometer, VAC will be equal to K into L1, or so E1 will be equal to KL1. Similarly, when key K2 is closed, keeping K1 open, then C2 be the balanced point. So E2 will be equal to VAC2, C1 and C2. That is VAC2 will be equal to KL2 and E2 equal to KL2. So we have E1 and E2. Now we just divide them. Now right here, dividing equation 1 by 2, what do we get here? We get E1 by E2 equal to KL1 by KL2. So E1 by E2 equal to L1 by L2. This is the relation between the EMFs of the cell that can be compared this way. That is how you derive this relation. You prove this application. Now we have the second application of the potentiometer, and that is to determine the internal resistance of a cell. So to do that, it is very simple as well. As you can see, first you need to draw a potentiometer circuit, which looks like this, by the way. Rheostat, and then we have a cell whose EMF is to be determined. This one's drive cell, so right here, and then under this we have a resistance box, which is also connected to the key. I'm kind of confused. Let me see. Yeah. Key, with this being primarily right here, and after the here there is a key K1, just like that. That is the circuit diagram required. So you just write some language. Consider a potentiometer with driver cell E0, rheostat RH, and connected with a two-way key K. There is a drive or a cell whose internal resistance is to be determined. This is the AB, by the way. Whose internal resistance is to be determined, just like that. A galvanometer G is placed with jockey as shown. A resistance box with key K1 opened. Okay, now first the key K1 is opened and balanced point was observed to be at C1, that is VAC1 was equal to of course KL1, and E now will be equal to VAC1, which will be equal to KL1. This is equation 1. Again, when key K1 is closed, now the key is closed, the key K1 is now closed, then the balanced point shifts to C2. That means VAC2 will be equal to KL2. You know that, right? Or V now it will be V because there is no other cell. V equal to VAC2, which will be equal to KL2. Equation 2 from equation. Okay, so from equation 1 and 2, if you divide them, you will get like this. 1 and 2 dividing, if you divide them, the equation 1 and 2, if you divide the equations, then what happens here is, if you divide 1 by 2, by the way, 1 by 2, E by V equal to KL1 by KL2. K cuts off. E means IR plus R and V is just IR, equal to L1 by L2. Now we need to cut the I's because I's are same, I and I. So R plus R by R equal to L1 by L2. This will also cut off, remaining with or this is also cut off, remaining with 1 plus R by R equal to L1 by L2. And if you do the, if you take the one other side, L1 by L2 minus 1 times R will be equal to R, and this is the relation for the internal resistance of a cell. And yeah, you can determine it by using this method. So yeah, that concludes the application of potentiometer. And now we're going to galvanometer. We have the numericals of this, so we are now going to numericals first before we go to galvanometers and others. So first of all, we go to the numerical part. And before that, we need to know some short questions as well. Some short questions why should the EMF of driver cell be greater than EMF of the test cell? EMF driver cell must be greater, because if that will be less than the EMF of a given cell, balance state cannot be achieved. What is the question again? Why should the EMF of driving cell greater than that of test cell? The answer is to obtain balanced condition. That's it. You need to know that much. And now that you know that much, you can basically go to the numericals. So here we have a very 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 shit ass long question. So I'm going to copy it very fast like a rapid hero, and then I'm gonna show you what's happening in it. So let me pause it. Okay, this is the question. Read it very very carefully. The driver cell of potentiometer has an EMF of 2 volt and negligible internal resistance. The potentiometer wire has a resistance of 3 ohm. Calculate the resistance needed in series with the wire if the potential difference. Look at this. The driver cell of a potentiometer has an EMF. First of all, write that. The driver cell of a potentiometer, the E naught is given 2 volt, and the negligible internal resistance R is 0. The potentiometer wire has a resistance of 3 ohm. The potentiometer wire resistance, the wire resistance is 3 ohm. Calculate the resistance needed in series with the wire if a new resistance, if the potential difference of 5 mega ohm, megavolt, if the potential difference I think it's not that the potential. Okay, yeah. If the potential difference of this much, this is milli. This is millivolt minus 3. That means, so the potential difference V is 5 into 10 to the power minus 3 volts. Required across the whole wire. The wire is 100 meters long, and the no, L is equal to 60 centimeters, and the wire is 100 centimeters long, I think. Yeah, it is not meter. 100 meter is a bit impractical. Okay, yeah, 100 L is 100 centimeters. So the resistance R we need to find out here is, let's do it question mark, as you can see. So now the main question here basically is, what do we have to do now? What is the main goal of this? So first of all, we know that the current I, we can use the relation of current with the VR, V equal to IR. So V equal to IR, so I will be equal to V by R, and this will be equal to, we won't use a V here, we'll use E by R. So E naught plus RP plus R, uh, E naught by RP plus R plus R. This will be equal to 2 by this is R plus 3 plus 0, that will be 2 by R plus 3 amperes current. Again, we know that V equal to IR, or V here is now 5 into 10 to the power minus 3 equal to 2 by R plus 3 into R. From here you can find the value of R. 5 into 10 to the power minus 3 equal to 2R by R plus 2 plus 1 by 3, I think, right? It is going to be um, what am I doing, bro? Yeah, if you split that, this is 2r, right? So can I split the denominator? 2r by r plus 2r by 3. Yeah, 2r. If you take the LCM, it will be the same thing. So yeah, I can do that, and I can absolutely cut this r, and 5 in 10 to the power minus 3 minus 2 times 3 by 2 will be equal to r. This is value of r. Let's see how much r will come to be. 5 into 10 to the power minus 3 minus 2 into 3 divided by 2. Okay, I think we messed up a bit. I think this is not the value ideal for the r. So let's check what's the mistake in here. Okay, let me check from my copy. Here is a sample numerical I've done. V equal to IR, right? V equal to IR. Okay. V is equal to IR P as well. So the negative. The mistake here is 5 in 10 to the power minus 3 equal to 2 by R plus 3 into resistance of the potentiometer wire is 3. And that will make it R will be equal to 5 in 10 to the power minus 3 divided by 3 into 2 equal to 1 by R plus 3. If you reciprocal this, that is 3 by 5 in 10 to the power minus 3 into 1 by 2 minus 3 will be equal to R. Now if I do that, 3 by 2 by 5 into 10 to the power minus 3 minus 3, that's 297 again. What is still not right, bro? Something's still not right enough. Of course this is not right enough, because this will be in the same thing. So this will be 6 divided by 5 in 10 to the power minus 2 into 2. R will be 1197 ohms. Now that we have R, we know that L of potentiometer is 100 centimeters. The balanced point is L is equal to, at what is it, at 60 centimeters, the VP, the potentiometer, that is 5 into 10 to the power minus 3 volts, and we need to find the E equal to what? We know the application. From the application, to determine the EMF of the cell, we know that E by BP equal to L by LP. That means E will be equal to 5 into 10 to the power minus 3 divided by VP is 5. VP, this is not, yeah. E by 5 into 10 to the power minus 3 equal to L is 100 by 60. So that would make it E equal to 5 into 5 into 10 to the power minus 3 divided by 3. Yeah. So that will be 5 into 10 to the power minus 3 into 5 divided by 3. That will not be what's the answer actually. It should be 60 by 100. Ah man, what is the relation anyway, bro? Here it is, the relation. E by V is L1 by L2 minus R. So that should be opposite, I guess. This is the answer, okay. Headache giving type shit, bro. I'm really not I don't really have expertise in these numericals, so I think we should it's better to just skip these numericals for now, because if we do not skip these, I'll just get bored and the video will end. So yeah. Yeah. Now we're going to galvanometer, and from that the video will come in the next video. The potentiometer numericals will also come in the next video, and this is the end of the video. So yeah, peace out. Bam.